The idea that a scientist like Maiman could invent something without any obvious practical use might appear to some as a waste of time and money. But the laser's invention has led to several widespread technological developments many of us take for granted. Soon after its first demonstration in 1960, the laser was used to transmit sound and gave proof that Maiman's device had the potential to change the world. Professor David Hanna is Emeritus Professor of Optoelectronics at the EPSRC Innovative Manufacturing Research Centre for Photonics.
Once people learned about the laser, about its existence, every scientist would think, what will that do for me? And so they would all pile in and say, look, we can do this, we can do that, and so on. So there'd be some people saying, look, we can get such a high intensity, we can make a star in the laboratory. Someone else would say, with a very high frequency like that from a laser, it means that the communications limitations of information carrying capacity are now suddenly released by a factor of 1,000,000. So we can send 1,000,000 times more information than we could before.
Today, lasers are commonplace, and for most of us, their use goes unnoticed.
We all have lasers now. We have lasers in the home. We have CD players, DVD players. We have communications via fibre, not coming right into the home, but out into the street. That's all done with lasers. Of course, you've seen probably film of laser robots welding together the bodies of cars. The supermarket is full of products which have been marked. That's usually a laser marker has done that. You do see the laser when you get to the checkout. It's not powerful enough to be a problem, so you can't cover it up because it has to be put onto the barcode.
In 1974, a packet of chewing gum became the first product to be bought using a laser-driven barcode reader. While in 1982, Billy Joel's album 52nd Street was the first to be etched onto a CD using a laser. However, the laser's use in medicine has seen some very different applications evolve. Dr. Kate Lancaster is from the Science and Technology Facilities Council's Central Laser Facility in Oxfordshire.
People's eyesight have been improved by lasers, for ages. Laser surgery has been around since the mid-80s. That's, de rigueur. And also there are sort of applications being developed called photodynamic therapy, for example, which is a way of treating cancer with laser photons in conjunction with special chemicals. And so, there's a very broad range of applications for lasers in medicine at the moment, and also things like tattoo removal and kind of skin improving, sort of cosmetic surgery has been greatly enhanced by lasers.
As well as medicine, modern lasers form the backbone of information technology and worldwide communications. Today, laser-based industries are worth billions of dollars annually. Tim Holt, Chief Executive of the Institute of Photonics at the University of Strathclyde.
It's a $7 billion business, the laser business, and it's enabled all these different products and processes and advances to be made in so many different areas. And in 50 years, it's incredible that has happened so quickly. And I can't think for the next 50 years about what advance we made in the future. But if it goes on the rate it's going, then the world will change completely in the next 50 years because of the laser.
Of course, whether or not the next 50 years will benefit from our use of lasers is largely dependent on the willingness to fund the research needed. The future is also dependent on other technologies keeping up. High-speed global communications using lasers only became possible with advances in satellite and microchip technologies.
The very first lasers were pretty clunky, large, inefficient, and so when you talk about a solution in search of a problem, it was really the technology was the problem. If you had a laser that could do something remarkable, but it filled half a room and cost $1 million, it wasn't going to make a big change to the world. But then when semiconductor lasers came along, this is taking a leaf out of microelectronics, and so the semiconductor laser is very much analogous to the minute component in an electronic circuit. And we all know how that led to a fantastic reduction in cost. When that happened with the laser, then it really took off.
With such a significant reduction in costs, the potential of lasers to solve some of the world's problems, especially in the field of energy supply, becomes a more realistic proposition. The Vulcan laser, based in Oxfordshire, is one of the highest intensity lasers in the world and gives those like Dr. Kate Lancaster access to some of the best facilities available.
We're trying to investigate how to generate miniature stars in the laboratory. And when I say miniature star, I mean trying to recreate the energy source of the sun, which is called fusion. And you kind of need really big lasers to do that. And there's one facility at the moment in California called the National Ignition Facility. That's capable of producing, well, it will be capable of producing 1 star a day. That's no good for energy production because you actually need to do 4 stars a second. So we have a project in Europe that will hopefully take the information and then run with it and develop the laser technology that you need to be able to fire these high power lasers 4 times a second in order to build a power station. So at the moment we're in a kind of critical phase where we're trying to get some money to do the 7-year sort of deep study to try and develop these high repetition diode pumped solid state lasers, as they're called, in order to build this facility. And hopefully if all those pieces come together, then HYPER will be built around 2025.
Central then to the success of HYPER is the willingness of European governments to increase the financial support required for research to continue, research which Kate believes is currently underfunded.
We need people to sit up and take notice and understand that this small amount of money, relatively small amount of money, is a small amount of money for long-term energy security for the rest of your life.
I think we have a very good record of funding in this country. The lab where I worked, the Optoelectronics Research Centre, received a large-scale funding from the funding bodies. It has led to things like the erbium-doped fibre amplifier. These amplifiers are used in the optical fibre communication system. They're out there, and funding from the EPSRC went into that work. And that's the sort of thing which really has a long horizon. You need to work on this for many years before it comes to fruition. But it is a great success story. It's out there powering up the internet.
With hindsight, it's easy to take for granted the laser's vast range of applications. But science agrees on one thing. As well as working towards hard and fast uses, the pursuit of open scientific exploration is equally valuable, just as it was back in 1960.
It's important to keep funding, well, certainly the laser research, because you don't know what's going to come out of it. The possibilities of producing different types of lasers, less expensive lasers, higher efficiency lasers, which will open up even more applications, is unknown unless you start to do the research. It's a chain. You've got to put the money in the front end in order to get the money out the other end.